Hey everybody. So today I wanted to talk about the situation where we want to derive a probability distribution from essentially two pieces of information. We got a formula which relates, say, two independent random variables to a dependent random variable, and then we have probability distributions associated with those two independent random variables. So we want to take all that information and from it derive a probability distribution for the dependent random variable. And so this is material that we went over in class, but I want to extend what we talked about in class a little bit, and then also go through some more worked problems. So a lot of this material will look will look familiar because we've been over it at least one time, if not more. Okay, so let's get the screen share going. All right, here we go. So remember the situation, and I more or less said this verbally, but let's kind of look at it in mathematical form. So we've got a function g, it could be our formula, which relates a dependent random variable that we're interested in sort of developing a probability distribution for, which is expressed essentially as a function of two independent random variables, x and y, for which we know the probability distribution. And so, again, this the y and the x are going to be our independent random variables. And z is a new random variable, which is going to be that arbitrary function of the random variables x and y. So, this is really, as I mentioned in class today, it's just an extension of kind of what we do almost every day, right? So we are given a formula, or we derive a formula, and we basically will plug some values in to for the variables on the right-hand side of the formula, and then we'll get an estimate for the value of the dependent variable on the left-hand side, and then we'll box the answer. But of course, the real world doesn't always work that way, right? There aren't always single values of x and y we can plug in, and we don't always get back a single value of the dependent variable. In reality, more likely, there's going to be some uncertainty associated with x and y, which is logically represented as a probability distribution, or two probability distributions. And so what we really would like to do then is take that information about the uncertainty, that is the probability distributions for x and y, and then translate it through the function g into a probability distribution for z. So instead of taking a single value of x and a single value of y and calculating a single value of z, what we're doing is we're taking probability density functions, or distributions for x and y, and calculating or deriving probability distributions for z. So that's the big picture. Another way to say it is, or kind of the big challenge here is, how do we derive the probability distribution for the random variable z, given probability distributions for the random variables x and y, and the functional relationship between them? Well, the first thing we have to recognize is that basically, if we're interested in an event, a very specific event for z, the random variable z, that is, we want to know, say we've isolated the event where random variable z is equal to some specific value z, little z. That's going to be the union over all combinations of xi and yj, that when we substitute them into our function g, we get back that z value. And so then the joint events where the random variable x is equal to xi and the random variable y equals yj, those joint events, when then unioned across all combinations that give you g of xi, yj equal to z, will then be corresponding to the event random variable z equal to little z. And of course, this is the case for discrete random variables. So I'm going to start with the discrete random variable case and go to the continuous random variable case. And you can see that because I'm talking about specific values of xi and yj when plugged into g give us z. If this is the relationship between an event in z and then the corresponding events in, or joint events in xi, yj, it makes sense that the probability that the random variable z is going to be equal to z, that is the probability that this event will occur, is going to be the sum over all combinations of xi and yj that when g is operated on them give us z. of the joint probabilities associated with those xi, yj. So we're summing up all of the joint probabilities over the xi and yj that when plugged into G give us C. The corresponding CDF, of course, would just be the sum over all combinations. Again, looking at the sum of the probabilities, the joint probabilities for random variable x and y being equal to xi and yj, summed over all combinations of xi and yj when plugged into G give us a value which is less than or equal to z. So basically that's going to correspond to the probability of all of those events, random variable z being less than or equal to little z, or a specific value z, which of course is just the definition of the CDF for z. So we can do an example, or at least kind of go through one formula, which is quite straightforward. That is the case where the random variable z is just equal to the sum of random variables x and y. And again, remember, this is for the discrete case. And so basically, we apply that formula that we obtained on the previous slide. We basically say that the probability that the random variable z is going to be equal to a specific value of z is equal to the sum of the joint probabilities for random variables x and y being equal to xi and yj for all combinations of xi and yj that sum to z. Now, as I mentioned in class, this is kind of an awkward notation here, and so we can rewrite it by simply solving for one of the variables, one of the independent variables, say yj. We can express yj then as yj is equal to z minus xi, and then just sum over all xi. So we're going to sum over all xi, and for each xi value in the sum, we're going to compute the corresponding yj value through this formula, which obviously depends on z. In fact, really the right-hand side only as a whole only depends on z, because once you specify the value z, you then will specify the sequence of yj's that you're going to get as you sum over all xi. And so this would be the case, or the sort of PMF, the derived PMF for z, given the PMF, the joint PMF for x and y, and then again summing over all xi and substituting that z minus xi for y here. Let's go through some more specific examples. So consider the case where x and y are both Poisson processes, and they are both independent random variables. And that'll become important in a bit later. So when we say they're Poisson processes, basically what we're saying is that the PMF for the random variable x and the PMF for the random variable y are both can be expressed in terms of Poisson PMFs. And basically you can see the parameter values have changed here. For the random variable x, I have an occurrence rate of nu. And in the case of the PMF for the random variable y, the occurrence rate is mu. And otherwise, everything is straightforward. Remember what the Poisson distribution represents. Basically, it tells us the probability that we're going to get a certain number of events, say random variable x, which stands for events, equal to a very specific number of events, given an occurrence rate nu and over a time t. Likewise, for this case, we'd be looking at the number of events we're going to get for the y variable, y equal to a very specific number, little y, oops, go back, given an amount of time t and an occurrence rate mu. So anyway, these are our two PMFs, one for the random variable x, one for the random variable y, and we've got our formula, which basically says that the derived PMF for z, under this circumstance where we have just the z equal to the sum of x and y, is going to be equal to the sum over all x of the joint PMF for x and y, where we've substituted for y this z minus x. So we actually now will take advantage of another one of the statements in the problem here, we said that the variables, the random variables x and y, were independent random variables, and that means that their joint PMF, the PMF for x comma y, is just going to be the product of the PMF for x times the PMF for y, again evaluated at the appropriate points. So the PMF for x is just going to be evaluated at x. The PMF for y is going to be evaluated at this z minus x position here. And so now that we've got our sum worked out and we've taken advantage of the fact that these independent variables are, the random variables are independent, we can go ahead and substitute in our PMF for x and our PMF for y, the Poisson processes for those two random variables, and we end up with this expression here. I've just simply substituted in the PMFs into the sum, so I haven't really done anything. Now I'm going to move that expression, it's exactly the same expression, up to the top of the next slide here. And now I'm going to just do a little bit of algebra. So I recognize that e to the minus nu t and e to the minus mu t does not depend on x, so I can pull that out of the sum and consolidate. So I get e to the minus nu plus mu t. Furthermore, I notice that I've got a t here and I've got a t here. This t is raised to the x. This t is raised to the z minus x. When I multiply those out, the x and the minus x will cancel out, and so I'll just be left with t to the z, which also doesn't depend on x, so I can pull that out of the sum as well. What I'm left with then inside the sum is this nu to the x times mu to the z minus x. Remember what nu and mu are. Nu is the occurrence rate for the random variable x, and mu is the occurrence rate for the random variable y, divided by x factorial times z minus x factorial. So that's all fine and good. We notice too, though, in the denominator, this x factorial times z minus x factorial looks a little bit like the binomial coefficient. If we were to write the binomial coefficient for z and x, it would be z factorial over x factorial times z minus x factorial. So I can multiply the sum top and bottom by z factorial, and then I will be able to replace this x factorial times z minus x factorial with the binomial coefficient, but I also have to have this extra z factorial term here, which I pulled out of the sum because it doesn't depend on x. And so the last trick that we can employ in this particular problem is the fact that this sum here is actually, from the binomial theorem, equal to nu plus mu to the z. So it's just a fact that if you had this quantity, nu plus mu to the z, I think we can thank Newton for this realization. You can rewrite that as an infinite series with the binomial coefficients zx, nu to the x times mu z minus x, mu to the z minus x. So anyway, this whole sum can be replaced with nu plus mu to the z. And when I do that, voila, I've got my new derived PMF for z. And if I just do a little bit of rearranging, kind of move things around a little bit, I get this result. And this is a nice way to present the PMF for z, because you will probably recognize it as the Poisson PMF with a new occurrence rate, which is nu plus mu. So it's exactly the PMF for the Poisson distribution, but our occurrence rate here is nu plus mu, which is kind of cool. I guess I want to say a couple things. The first thing I want to say is that we've derived this PMF for z, and it doesn't depend on the PMF for x and the PMF for y, or you don't see an x and y in this distribution at all, except for the fact that you can see their occurrence rates have now sort of been embedded in this new derived distribution. So the distribution itself only depends on z, right? So z's in the exponent here, and they've got a z factorial, and obviously the amount of time that's elapsed, but doesn't depend explicitly on x and y, except through the occurrence rates for x and y, that is nu and mu. The other thing I want to say is that that last result can be generalized. So if I have a discrete random variable z which is essentially the sum of an arbitrary number of discrete independent random variables. So again, we've got this independent criteria. So basically, I can express the random variable z as the sum over n of the random variables, independent random variables xi. Then it turns out that if these xi are each a Poisson process, then the random variable z is also a Poisson process with a rate of occurrence nu z, which is just equal to the sum of all of the occurrence rates for the individual independent random variables on the right-hand side here, nu I. So basically, it's a generalization of our result here, where we had two independent Poisson processes, one for x and one for y, which had an occurrence rate of nu and mu, and then basically the derived PMF for the sum of those two independent processes, that would be z here, the PMF for z, was just again a Poisson process with the occurrence rate being the sum of the individual occurrence rates. So that's just a generalization to say that that result that we showed for two independent variables, x and y, can be extended to any number of independent variables being summed together that are statistically independent. The book also points out that while this works for the sum of two or more Poisson processes, it does not work for the difference of two or more Poisson processes. So we can't get away with taking the difference of two independent variables that are Poisson processes and assuming that that difference is going to also be a Poisson process. So only for the sums. Okay, so we went through this example in class. We've got a toll bridge here, which is serving 3 suburban residential districts, A, B, and C. And during peak traffic hours of each day, the estimated average volumes of vehicular traffic from the 3 districts are respectively 2, 3, and 4 vehicles per minute. Assume that peak hour traffic from each district can be assumed to be a Poisson process with respective parameters or occurrence rates of 2, 3, and 4 vehicles per minute. And we're asked to A, derive a PMF for the total peak hour traffic at the toll bridge. Okay, so we understand that basically the peak traffic at the toll bridge, kind of by car conservation or mass conservation, is going to be the sum of the cars coming from districts A, B, and C. So we've got a formula which is essentially saying that the new dependent variable, say the random variable for cars crossing the toll bridge, we might call it big T, is equal to the sum of the random variables for the number of cars being generated by A, B, and C. And we know A, B, and C are a Poisson process, which means that their sum is also a Poisson process. We just showed that. And not only that, but we also showed that the new occurrence rate for that new derived Poisson process is just the sum of the occurrence rates for the individual statistically independent random variables, in this case A, B, and C. So putting it all together, then our answer is basically that our, I guess we're going to call it sub C. Anyway, the PMF for cars crossing the toll bridge in this case is just going to be equal to nu times T raised to the C, the number of cars, over C factorial e to the minus nu T. This is just the Poisson distribution applied to cars crossing the toll bridge. The key bit here is that the occurrence rate is just going to be the sum across the occurrence rates from the different districts, which works out to 9 cars per minute. So that's the answer to part A. And then we were asked in part B to determine the probability of 9 or more cars passing the toll bridge in 1 minute. And of course, that's going to be the complement of the probability of less than or equal to 9 cars passing the toll bridge in 1 minute. So the probability that the number of cars crossing the toll bridge is greater than 9 is going to be 1 minus the probability the number of cars crossing the bridge is less than or equal to 9, which is going to be 1 minus the sum then of this PMF, where C is going from 0 to 9. Now, I highlighted the C equal to 0 because we did this correctly in class. We basically recognized that one of the sort of events that would correspond to c less than or equal to 9 would be c equal to 0. That is, there are no cars crossing the toll bridge in 1 minute. And so we summed from 0 to 9. I just wanted to point this out because in my notes, my class notes, this was c equal to 1. So even though I was arguing in class and writing on the board that this was c equal to 0, in fact, on my slides, it said c equal to 1, so I apologize for any confusion. Anyway, if you work this out, it works out to be 0.413, so about 41.3% probability that 9 or more cars will pass the toll bridge in 1 minute, given these occurrence rates or vehicular traffic rates for the different districts, A, B, and C. Okay, so now let's kind of apply the same theory or the same ideas to, instead of discrete random variables, now we're going to apply it to continuous random variables. And let's start with the CDF, the cumulative distribution function. And so what we want to do is write out the cumulative distribution function for that dependent random variable z based on some understanding of the joint probability distribution for x and y, and then the functional relationship between z and x and y. And really, just by definition, we can say that the CDF for the random variable z is going to be the sum of the joint PDF for x and y, random variables x and y, integrated over all combinations of x and y that when plugged into G are equal to or less than Z. So that is the essentially the definition of the CDF for Z. And you know, like we kind of had an indexing issue with the summation when we were talking about the discrete variables a few minutes ago. We kind of encountered the same thing. This is a really awkward notation for the integration. I mean, so we're essentially integrating this double integral over all combinations of x and y when plugged into G give us something that's equal to or less than Z. That's very awkward. We'd like to make it a little bit more explicit. And what we can do there is we can basically take one of those independent variables, either x or y, in this case I'm taking x, and we can essentially solve for it by applying the inverse function to y and z. So I'm just kind of applying the inverse function to y and z so I can isolate x there. In practice, we'd have to solve, depending on what the formula that G represented, we just have to solve for x. In that event, basically, what we can say is that we can determine x based on you know, whatever the value of z is that was plugged into the left-hand side of the equation. That's fine. And then all values of y over the domain, which runs from -infinity to infinity. So we're basically going to integrate over all of y, which is -infinity to infinity. And for each value of y in this integration, we're basically going to calculate the upper limit based on the solution x equals g inverse of y comma z. So essentially we're determining each value of the upper limit here based on the value of z that's been given, and then the value of y that we're integrating over in the outside integral. So we could have just as easily solved for y as an inverse function g of x and z. There's really no reason why it has to be x here. It could just as easily have been y, in which case our CDF for z looks exactly the same, except we're just switching the order of integration. So the outer integral is with respect to x, the inner integral is with respect to y, and that upper limit for the integral with respect to y is going to be y equals g inverse x of z in this case. So both of these are absolutely equivalent. It doesn't matter which way you do it. And so we can basically say then that the CDF for z, that is the probability that the random variable z is going to be less than or equal to a specific value of z, is equal to this double integral evaluated where we're solving for x in terms of the inverse function of g, or the double integral where we're solving for y in terms of the inverse function of g. So now that we have the solution for the continuous random variable CDF, we can essentially calculate or determine what the corresponding PDF would be by differentiation. So let's take the first case, we're calling it version 1 here, where we start with the CDF, in which we solve for x as an inverse function of y and z. So that was just one of the 2 options we had. So we're going to call that version 1. And now we're going to say, hey, look, I can calculate the corresponding PDF for the random variable z by just differentiating the CDF with respect to z. And so I just differentiated both sides of this equation. So I've got the derivative here with respect to z. And I also recognize that the outer integral here with respect to y doesn't depend on z, so I can bring that derivative inside that first integral. And now I have to evaluate this derivative of this thing, because you can see that in the upper limit I've got a function of z. So I can't bring that derivative inside the integrand here, because this integral actually depends on z. And so what I do is I apply the chain rule, right? So I basically say, okay, I'm going to take the derivative with respect to z of this integral, which means that I'm going to take the integrand, evaluate it at the upper limit, and then multiply that by, through the chain rule, the derivative of that upper limit with respect to z. And that's what I've got here. So basically, I've got the integrand, which is my joint PDF in this case, evaluated at x equals g inverse of yz, times then the absolute value, because we have to remember we have this issue of whether g is an increasing or decreasing function of y and z. So just to avoid that issue, we have these absolute values here. So now we've got the partial derivative of g inverse of yz with respect to z. The reason we have to use partials here is because g inverse is a function of both y and z. So there's our derived PDF for the random variable z, in terms of, or based on, the joint PDF for x and y, again, and the formula that relates x, y, and z. Alternatively, we could have gone with version 2, where we express the CDF for z in terms of y instead of x. It's perfectly equivalent and the same, and we basically go through the exact same sequence, just reordered the order of integration here. And so when we take the derivative of the right-hand side there, we bring it in, and then we've got exactly the same thing, except this time, when we evaluate that derivative, we're going to basically evaluate the joint PDF for x and then y equal to g inverse of xz here, and then take the derivative again of that g inverse function with respect to z. So it's essentially the same. And so basically, here's the summary. We've got derived PDF for z based on the joint PDF for x and y. And then we have one version of this formula if we solve for x in terms of g inverse of yz, or another version of the formula if we solve for y in terms of g inverse of x and z. Okay, so let's do an example, maybe make this a little bit more concrete. So remember, for the discrete random variable case, the kind of first formula we looked at was the sum of 2 independent random variables. So we're going to basically do the same thing here. We're going to look at the function g being the sum of 2 continuous random variables x and y. And then we're going to also add in the fact that they could have constants a and b. So this is what our formula looks like. So we're interested in deriving a PDF for the random variable z, given PDFs for the random variables, or the joint, I should say the joint PDF for x and y, random variables x and y, and also this formula, which is basically saying that z is equal to the sum of the x and y weighted by constants a and b. So if we take the first version of the PDF for z, basically this is our formula here. So what do we need to do? First, we need to evaluate the g inverse of yz, and then we need to compute its derivative with respect to z. So in this case, we're solving for x is equal to g inverse of yz. So if we look back at our formula and we solve for x, that's going to be that x is equal to z minus by over a. And I think that's what I have here. Yep, x is equal to g inverse of yz, and that's going to be equal to z minus by divided by a. I'm just rearranging this equation, solving for x to get this particular form of the inverse function for my kind of version 1 of the PDF. Now that I've got my inverse function, g inverse of yz, I can take its derivative with respect to z. And of course, this is just a constant with respect to that derivative. And so I'm going to be left with 1 over a, because I'm just going to have the partial derivative of z over a with respect to z, which is just equal to 1 over a. So this is the quantity that I need to substitute in for x in my joint PDF. And this is the quantity, 1 over a, that I need to substitute in this case, for my derivative of g inverse of yz with respect to z. And so there you go. So for this first version of the PDF, I have my derived PDF for z is just equal to 1 over a, integral from minus infinity to infinity of the joint PDF, where x is replaced with z minus by over a, and then we're integrating with respect to y. All right, so likewise, we could have gone with version 2 of the PDF. Remember, these are all equivalent, just different ways of essentially writing the same thing. In that case, we're solving for y in terms of the inverse function acted on x and z. And so then in this case, we need to determine what that g inverse function is in terms of x and z. And that's just obtained by solving for y. And we can see that's going to be z minus ax divided by b. And there you go. So y, which is in the g inverse function of x and z, is equal to z minus ax over b. And then if we take the derivative of that right-hand side with respect to z, we just get 1 over b. So 1 over b goes in for this absolute value term here, and then we substitute for the g inverse function, we substitute this quantity quotient c minus ax over b. And there you go. So there's the derived PDF for z in the case where we go with version 2 of the PDF. And so here's your result. Again, for the case where the random variable z is just the sum of random variables x and y weighted by a and b, you get 2 absolutely equivalent ways of deriving that PDF for z, either in terms of the substitution for x or the substitution for y. And if you had a very specific, say, joint PDF that you were evaluating, what you'd find is that it didn't matter. It wouldn't matter whether you used this formula or this formula, you would get a goal. The other key thing to recognize is that this is a joint PDF. And so it's tracking how the probability density depends jointly on x and y. If x and y are independent, then you can break this joint PDF into the product of the PDF for x and the PDF for y, and that's sometimes convenient. And likewise, we would have the corresponding situation for the version 2 that I went through, where again we've just broken this joint PDF into the product of PDF for x and PDF for y. All right, so let's go through now a specific application of those ideas. This is example 4.8 in the textbook. So the problem reads as follows. The figure below shows the frame of a building subjected to earthquake forces. The building mass M is assumed to be concentrated at the roof level. When subjected to ground shaking during an earthquake, the building will vibrate about its original at-rest position, inducing velocity components x and y of the mass with a resultant velocity z. And so basically what we're doing is we got this building, so we're kind of looking at it from the street level. It's got a roof with a lot of weight on the roof. And then if we looked down on the roof, would be what we would see. That's the plan view. And so after an earthquake, basically this building is oscillating. and it's generating essentially velocities in the x and y with a resultant velocity z. And you know, from vector mechanics, we know that the z is just going to be square root of the magnitude of z here is just going to be the square root of x squared plus y squared, essentially the modulus of z. And we can also recognize, or we can treat x and y as random variables, in which case essentially what we're doing is we're saying this, this random variable for z, the resultant velocity vector, is going to be essentially this formula related to x and y, the x and y components through this formula. Okay, so that's a bunch of mumbo jumbo. Moving on, we say assuming the x and y are statistically independent standard normal variates, n0, 1, determine the probability distribution of the resultant kinetic energy of the building during an earthquake. So we want to calculate the kinetic energy, which is going to be equal to the mass m of the roof times the velocity, the sort of resultant velocity z squared. But we know this relationship, we sort of, from vector mechanics, we know this relationship between z and the components x and y. And so if we plug that into z squared here, we're saying basically that the kinetic energy is the sum of x squared plus y squared multiplied by m. All right, so we need to solve this sucker, and here's how we're going to do it. And this is a bit of a complicated problem because it sort of involves multiple steps. I think problems that involve multiple steps are always a little bit difficult to get your head around, but it's totally doable. So basically, this is the information that we're given. We're given the expression for the kinetic energy, which is our formula that we need to use. So that's the kinetic energy W there. And that's going to be a function of the random variables x and y squared times the mass. Furthermore, we know that x and y are standard normal variates, and we can write out then that the PDFs for x and y are going to be like so. This is just the standard normal variate, meaning that it's the normal distribution with a mean of 0 and a unit standard deviation. All right, so that's all fine and good. That's what we're given. Now, the tricky part of this problem is that actually it builds on a result from example 4.5, where we showed, you may not remember this, but we showed that if you had this formula for a random variable, dependent random variable as a function of a single independent random variable, that is s squared, where c is just a constant, if you had this particular formula for g, and you assumed that the probability distribution for s was again a standard normal variate given by this PDF for s here, we showed that basically these two pieces of information, when we sort of calculate or derive the PDF for u, it ends up being a chi-square distribution. And so basically, we know that this relationship, this formula here, plus a standard normal variate, gives us the chi-square distribution indicated here. Why is that relevant? Well, you can see that this equation that we're working with here is the sum of mx squared plus my squared. And so basically, we already know then what the PDFs are going to be for mx squared. It's going to be somehow related to the chi-square distribution here, and also my squared, again related to the chi-square distribution. Let me be more specific. So basically what I'm trying to say is that you could take, say, a new random variable, or define a new random variable u as being equal to mx squared. So I'm basically taking that first term there, mx squared. And then from this result here, we know immediately that the derived PDF for u is just going to be our chi-square distribution, where c is replaced with m, right? So there's m. And so that's going to be our PDF then for u. And likewise, if we defined v as equal to my squared, so it's the second term in our kinetic energy expression, we know immediately that PDF for v is just going to be equal to the chi-square distribution with that c there replaced with an m, because you can see m here is replacing the c. And so basically, we have then derived PDFs right from the get-go for essentially mx squared and my squared, which I'm calling u and v. The key point being that kinetic energy now can be expressed, of course, originally was mx squared plus my squared, but now we have PDFs for mx squared and my squared. And so basically we can express the kinetic energy then as a new formula, which is just the sum of those two new chi-squared PDFs. Okay, and why is that relevant? Because we just derived the situation where a random variable z is essentially a function of x and y, a specific function where x and y are summed together with constants a and b. And under those circumstances, we showed that for one of the versions of the PDF, that the derived PDF for z is just equal to this thing here. So that allows us to kind of plug and chug, because at this stage we've reduced that kinetic energy expression just to the sum of PDFs for u and v, which we know are chi-squared distributions. And so we immediately know then from this formula that the derived PDF for w is just going to be the integral from minus infinity to infinity. Here a is equal to 1 because the coefficient in front of u is 1. So it's just 1 over 1. So it's the integral from minus infinity to infinity of the first PDF. And again, these are statistically independent. So, and that's going to be f of u, right? And then evaluated at essentially the solution for x, which in this case was z minus by over a in our original solution. A is 1, b is 1 in this expression. So that becomes z, and z is w. Sorry, that's a little bit confusing. Hopefully you can figure it out. So that just basically becomes 1 w minus nu. So z minus by over a becomes w minus nu. And then for the second PDF, which is the PDF for v, it's just f of v, or little v, dv. Now, the only other thing that we need to keep track of is the fact that if we go back here, the chi-square distributions were restricted to argument values greater than or equal to 0. And so if we go over here, we've got our integral goes from minus infinity to infinity. And so you can see that basically for the dummy variable nu here, we don't want it to go below 0. So we're going to just get rid of everything that's negative. So it's just going to go from 0 instead of minus infinity. And then if we look at the upper limit, basically if you look at this argument, again, that's a chi-square distribution. And the argument of that chi-square distribution has to be greater than or equal to 0. And so that means that this upper limit can't be any bigger than w, because otherwise this argument would go negative. And so that restricts our upper limit to little w. Okay, so so now we've got a sort of an expression for the PDF, a derived PDF for w in terms of the PDFs for u and v. And remember, the PDFs for u and v are just the chi-square distributions. And so we can substitute those in, and after a little bit of simplification, we end up with this result. And this integral, we can essentially evaluate. The textbook goes through and shows its relationship to the beta distribution, but you can just simply do this analytically as well, for example, in Mathematica, and you'll find that the whole integral here just equals pi. And so the pi's cancel, and you're left with the derived distribution for the kinetic energy of e to the minus w over 2m divided by 2m. Okay, so it was a lot of effort for a very, very simple result in terms of the probability distribution of the kinetic energy on that roof, which obviously could be really important if we were looking at the chances that the kinetic energy is such that the building would fail. So we definitely want to know how that probability distribution varied with, for example, the mass of the roof. Okay, so the textbook goes through some other key results along the same lines, looking at various kinds of sums and the corresponding PDFs for the independent variables. And one of the examples that they give, which I think is quite important, is this idea that if you have statistically independent normal variates, that if you sum them up and you weight them here, say with a coefficient AI, so our random variable z then is going to be the sum over a whole bunch of different statistically independent random variables, each weighted by AI. And again, where each of these xi are normally distributed with some mu xi and sigma xi, so mean and standard deviation for each of the random variables xi. The theory shows us that the random variable z is also normally distributed with mean mu z and standard deviation sigma z. And importantly, the mean can be calculated as the sum over all of the means for each of the random variables xi weighted by their corresponding coefficients. Likewise, the variance for z, from which you can obviously calculate a standard deviation, is going to be the sum over all of the variances for xi weighted by ai to the power of 2. So in this case, this is a bit of a difference. So for example, if you had like a minus one of these terms, one of these AIs was, say, a negative number, in the mean, what would happen is that that the mean associated with that negative number would subtract in the sum, whereas in this case, you can see that it's squared, so it would always add. So the variance is always increased, even if the mean can be decreased in some circumstances. So in words, basically what we're saying is that any linear function of Gaussian variates is also a Gaussian variate. It's just a really succinct way of saying it. It's also true that if you take the product of statistically independent log normal variates, so you define a new random variable, which is essentially just the product, which is what that pi means, so of a series of statistically independent random variables xi, where each of the xi are log normally distributed with their own lambda and zeta parameters. The theory basically shows us that the random variable z is also log normally distributed with these new parameters lambda z and zeta z. And lambda z, furthermore, is just the sum over all of the individual lambdas, lambda xi's, and the sort of corresponding variance of the log transform values, which is what that zeta means, zeta z squared, is just the sum of the variance of the individual xi's. So basically, these are quite useful. Frankly, I'm like on a final exam or any problem that I would give you, I'm really going, you can solve all the problems with that involve sort of sums of Gaussian variates using this approach. Even if I tell you that the variates are log normally distributed, because of course if you log transform the variable, then it's going to be normally distributed. So you can always get it in this form. And in fact, actually, this result here is a consequence of the fact that the log transform, if you have variables which are log normally distributed, the log transform of those variables is normally distributed. Okay, so I'm running out of power, so what I'm going to do is sign off for a minute and then get my computer plugged in, and then I'll pick it up and we'll go through a couple of examples. So see you in a second.